Welcome back to sections 20.1 through 20.4. In this video, we will write out the equations for fixed axis and fixed point rotation. They happen to be the same. Look at what happens with parallel plane motion. What if all, say, our motion is in two different planes that are parallel? What happens if our rigid body is undergoing translation only? Write out some perpendicular vector constraints, and then solve example 3, which is an example of a problem that rotates about a fixed axis. All right. So I've pre-written these equations for a fixed point or axis. So if we have a velocity or an acceleration, and we can, so this further simplifies the equations we had for general motion. So for general plane motion, we started with a translating and rotating coordinate system. We simplified that for the case where we had a constant length for the vector from A to B. This further simplifies that if modeled as something that rotates about a point or about an axis. It ends up being the same thing. What happens is our velocity A and our acceleration A go away, and then we get these terms. So now this is no longer a vector B, A to B, because A and O, the two base points of our two coordinate systems, are going to be on top of each other. So we don't need to put the subscripts in there. You can if you want. And then when you go and you do this omega cross R, make sure you do it in the correct order, and do not use the negative omega squared times R substitution. That is only for planar rigid bodies. You'll get the wrong answer if you do that. So make sure you go through the cross product in full. If you have parallel plane motion, so think like a clock on a wall, you have a bunch of gears in the back, turning some arms in the front, so you have motion in different planes. Well, that's all parallel to one another, so you can just use planar rigid body motion. So that's chapter 16 stuff. If you have only translation, so if you're told that the body only translates and doesn't rotate, well, then you're going to get the velocity B is equal to velocity A and acceleration B is equal to acceleration A. We have no rotation, so this becomes particle kinematics, so you can go back to chapter 12 for this kind of problem. And then the last piece that we need to write out is perpendicular vector constraints. So there are times when you're going to be solving a problem and you're going to have more unknowns than you have equations, and that might be a case where you need to constrain the problem so that you can figure out the answer. And one constraint you can use is to constrain, say, your generic vector A to be perpendicular to some R vector, some position vector. If they're perpendicular, then their dot product will be 0. So that's the generic form. So we can do this for things like velocity, acceleration, angular velocity. So I'll write out those three real quick. Alright, so those are written out now. So for velocity, you might find something like the velocity inside the A coordinate system, the local coordinate system. So that velocity of point B with respect to A, you might say that you need to be perpendicular to the vector from A to B. So you can do that dot product. The acceleration doesn't look like this form, because we get to acceleration through the derivative of this. So if I I drop my VB down, derivative of R is V, and then over here, drop the R down, derivative of V is A. So that's where this comes from. You can do a similar thing with angular velocity. So most of the time, you're going to be doing this with a velocity, so either a velocity or angular velocity, and then you can derive the acceleration or the angular acceleration from these. So this would be omega dotted with RBA. This will just state that the omega vector, so that we know how to find that now, is perpendicular to that R vector. So the direction of the rotation, the axis that it rotates about, is perpendicular to the vector to B and A. Alright, so let's look at an example of something that rotates about an axis. So we basically have this set up here, so I brought a nail. Fancy, look at that. See, it rotates about a point, and actually if we model this as a cone, because you could, so it's not actually a cone, then you would note that we have an axis down here. I'll do it in pink. That's an axis of instantaneous rotation. Basically, all points on that are 0. There is no velocity down there where it's rolling because it rolls without slipping. So by inspection, I have determined the direction of my omega vector. It has to be along that, because that's my instantaneous axis of rotation. Now, you also get these if you pin something, so like you can think like a pin joint or something. But in this case, we are rolling without slipping, so we get it, we know which direction it is, which is actually really useful. And in a way, we can actually model this whole problem as A, rotating about this point, So if you drew this in just this zx axis, you could actually model this as a planar problem. So let's find velocity A. So velocity A, we're just going to use our equations up here to find these. So I'll just rewrite them. So velocity A will be equal to the omega crossed with the vector to A. So I need to go find omega and vector A. I know which direction vector this is, so I know this is a j hat. So let's redraw this in 2D. So we're just going to have our y-axis and our z-axis. Again, we know that we aren't rotating about this axis. I have my center, and I have this vector that goes to that. So I'll mark that in yellow, so this one here. And then we have this line. This is perpendicular, so this is our center of gravity, or not really the center of gravity, but it's the center point of it. I wouldn't really call it G, but we know that this is 150 millimeters. We know that this is 300 millimeters. That's what we were told. Because this is perpendicular, I can just use trig here. I want to find this angle theta. That's angle theta. Well, this is the hypotenuse. This is the opposite, so it's just a sine. So theta will just be the sine inverse of opposite over adjacent. So I am doing this in millimeters, but the units cancel. So you can convert these to meters if you want. So you will find that theta is 30 degrees. Now if I continue this up for an equal amount, so another 150 here, and I come down, this is point A up here. Point A, well, we know that this side is 300. We also know that this side is 300 because it's just a mirror. Basically, we've mirrored this shape up here. So this is 300. This entire angle up here is 60 degrees. So if I redraw this one time, so up to point A, and this time we're going to do it this way so that I can turn this into my z and y coordinates. Well, this is 300. This is 60 degrees, which means that this is 150 and this is 150 root 3. So again, you can do your trig on that and you'll find that you have all that. So I can use this triangle to find RA and to find omega. So you could find omega by doing omega z plus the omega of this yellow bar. So you can do that. That's what the book will do. I'm just going to use trig to find it. So let's do that here. So RA, the vector RA, is going to be over 150. So there's nothing in the x direction. It's going to go over 150. So it's not the full 300. It only goes over 150 to get up to A. So I'm just going to do this in millimeters. We can convert to meters later if we need to. And then 150 root 3 to get up to A in the z direction. So that's our vector RA. And then omega, well, omega is about this axis here. Z is about this axis here. This axis is actually the same as this axis. I can relate those through this 60 degrees here. Now you do have to be careful with signs. You can't just put magnitude over magnitude. So basically I'm going to have my z go up. Why up? Well, I know that it rotates positive about that z-axis. I'm going to use right-hand rule, so I know that its axis of rotation points up, which means that it starts here. So this pink vector also has to start here, which means that if I'm going to do vector math, I need to make it go this way. And then I will come down so that I end at the same point. So this is our axis of rotation, and this hypotenuse line here, that's just this bar in the middle. So I don't actually have to find that. If you want to do vector math, you can find it. You'll end up with simultaneous equations for omega z. I would call this omega spin, and then you have omega down here. So you could do that, and that's what the book does. But I'm just going to use this 60 degrees to relate them. So it's tangent theta equal to opposite over adjacent. So our opposite being, so we'll have tangent of 60 degrees equal to the z, which is 0.5. And then omega, but I've made omega negative, so I need to make sure I put in a negative omega here. So these are just going to be magnitudes because I'm just doing a trig function and not a actual vector math. And then if you solve that, you're going to find that omega comes out to be a negative 866, which is actually negative root 3 over 2. So I'm just going to box these because I need to use them later. They're not answers. Let's go up here. You then say negative root 3 over 2. We know it's in the y direction, so we're going to put a j hat. And then we're going to cross that with our 0, 150, and 150 root 3. Remember, when you do your cross product, you can write out the full one, or you can use the I, J, K circle. That's what I prefer to do. So j cross with I is going to produce our k value, which is going to be 0. J cross with j produces our j value, which is 0, because they are parallel to one another. And then j cross with k, so j into k makes an I, so we'll get an I. And then we get 150 root 3 times root 3 over 2, which ends up becoming negative 225 if you do the math. So again, that was j into k, so we got a positive I, so we keep all signs the same. So that is that, and that is going to be in millimeters per second. If you want meters per second, just move your decimal point. Alright. And then let's squeeze our acceleration a in here. So acceleration of point A, that's going to be alpha cross RA plus omega cross omega cross R to A, using our equation from above. So we know RA, we know omega. So the only thing we have to do is find alpha, and we can solve this. To find alpha, alpha is just omega dot. So we're going to use the derivative of any vector equation. So that's going to be omega dot in the x, y, z coordinate system plus the rotation of that coordinate system crossed with omega. Again, I know omega. Well, this is 0 because I have constant rotation, so I have no local accelerations. I only have acceleration due to the basically two different things rotating in different directions. So in this case, what you can think of is I have my rotation kind of about that point at the bottom of this cone, but if I didn't rotate it, I'd basically be rotating my coordinate system about the z-axis, which would just be rotating that cone. And if you kind of just looked down in the xy plane, all you would see is that pink line just kind of sweeping around. So that means that this is just 0.5 k hat. Again, I know what this is. This is negative root 3 over 2, and that is a j hat. So then you just do your vector math. So you're going to cross a k into a j, and you're going to get an I. This is not intuitive. Your acceleration is actually in the I direction, and you will find that it is root 3 over 4 I hat after you do the math. Now note, you're going to have one negative sign here. Your other negative sign comes from the fact that you're going k into j, which is backwards on the thing. Alright, and so all we have left to do is just find alpha a. So let me copy this onto the back of the page, and then we'll finish up. Alright, so that's done. So we've taken what we know now, RA, omega, and alpha, and I've just copied them into this equation on the back. So root 3 over 4 I hat, our vector to A is just that, omega, omega, and then that vector to A. So this is just a math problem at this point. So you solve this, you're going to find that this chunk of stuff right here is going to come out to a 0, negative 112.5, and 75 root 3. And then you're going to find out that this stuff, make sure you do this, remember, do this cross product, then do the next cross product, and do not use negative omega squared r. Will come out to just be a negative 194.8 k hat is what you'll get out of this. When you put all that together, you will get that the acceleration of A is a 0, a negative 112.5, and then you're going to put these two terms together, and you're going to get a total of negative 129.8. And this will be millimeters per second squared. All right. So there you go. That would be the acceleration of the top point for that thing rolling around. Hopefully that helps. If you have any questions, feel free to reach out.